Okay, so I believe I should start today's session. So this is the second live tutorial session for the NPTEL's Fundamentals of Compressible Flow course. All right. So the instructor for this course, as you all know, is Professor Niranjan Sahu. He's from Department of Mechanical Engineering, IIT Guwahati. And my name is Aditya Sharma. So I will be the teaching assistant for these sessions. All right. So we already have been through one such session in which problems linked to week one topics were covered. All right. So in this session, we shall see the topics related to week two. All right, week two lectures, and few problems are there. So we shall also look into those problems, and we shall see how to proceed forward in such problems. All right. So let's move ahead in this session. All right. So first of all, we'll just briefly see what are the different topics. The different topics that have been covered in the week two lectures. Uh, that is lecture 4, 5, and lecture 6. The videos of these lectures are already available on the SWAYAM portal. All right. And we shall briefly discuss all the topics that have been covered in these lectures. All right. So, uh, in the lecture 4, so first topic that was covered was introduction to compressible flow. So, in this, uh, I'm sorry, just wait a minute. Okay. So the first topic was introduction to compressible flow. All right. In this, uh, hello Yogesh. Good afternoon. So I have already started the session. Just briefly, uh, not even briefly, I've just introduced to this session. So we shall uh, look into the topics of week two. Briefly, we shall, as was done in the previous session. So we shall go in that fashion only, and then we shall see various or different problems related to week two topics. All right, Yogesh.
Yes, sir.
Thank you, and thanks for joining. All right. So, lecture 4. So first topic was introduction to compressible flow. All right. So as we saw in week one lecture, so it was basically fundamentals of fluid mechanics. All right. There we were introduced to fluid mechanics and some concepts that we should know while we are trying to study compressible flows. All right. So in this week two lectures we step into the compressible flows. All right. So the first topic was introduction to compressible flow. So here we saw just definition of compressible flow and what compressibility is. So second topic in lecture 4 was compressibility. So two types of compressibilities were also discussed. All right. So I believe it was isothermal compressibility and isentropic compressibility is there. So and there were few formulae related to those two topics in compressibility only. All right. So basically, what we are doing, we are trying to define compressibility and what type of compressibilities and situations are there where there is compressibility. All right. So then we moved on to propagation in compressible fluid. So here we saw like if there in a stationary fluid, if we introduce some disturbance, so that disturbance how it propagates in that medium, just we looked into that aspect of wave propagation. All right. So here we were mainly concerned with 1D flows only, like it the wave is propagating in one direction only. So it's not even 2D or 3D. 3D compressible 3D like shock waves, if you see generally in real life, like in aircrafts also, we see 3D shock waves, all right, in front of aircrafts. So, but as we have just introduced, we have just stepped into this compressible flows course. So uh, we initiate with the 1D flows only, and then later, if we want to delve deeper into the subject, so we proceed in that manner. All right. So 1D flow was discussed. All right, and there were equations related to 1D flow. Different equations related to 1D flow were discussed. All right. And then there were compressible flow properties were discussed. All right. Properties this has already been introduced to some extent in week 1 also, the speed of sound. All right. So we had also one fill in the blank of this uh, topic or concept. All right. So compressible flow properties, we discussed acoustic speed and speed of sound. That is basically the speed with which a disturbance propagates if the disturbance, the magnitude of disturbance is not too large. All right. If it's infinitesimally small. All right. But then there are cases when the disturbances are traveling at speeds that are greater than the speed of sound. So in that case, how we study such situations, so that also will be seen in the coming topics, also in coming lectures. All right. So then another important non-dimensional parameter related to compressible flows is Mach number, which is nothing but velocity. All right, velocity of a disturbance or an object. It's a ratio of velocity, such velocity to the speed of sound. Okay, so that is Mach number. So later we have categorized flow regimes based on this particular non-dimensional property. All right, non-dimensional compressible flow property. Okay, so then we moved on to isentropic flows. So isentropy is nothing but where there is no change in the entropy. Literally speaking, isentropy is where there is no change in entropy. And what comprises of isentropic condition is the adiabaticity of the flow. That is, the flow has to be adiabatic. Also, the flow has to be reversible. All right. So these are ideal conditions, and
Still,
we
can I have
yes,
why when we come to this compressible flow, why we only
yes.
talk about isentropic, not that adiabatic and other type? Only why we talk only about isentropic
So
condition?
because such suppositions, right? So when we like currently, I'll tell you, I am working on shock tubes. All right. So the speed that we are discussing here, all right. So in that speed, it's a good supposition to say that the flow is adiabatic and reversible because it's too fast. So we can not a it won't be a blunder to compare isentropic situations to the real world flows, compressible flow problems that we encounter in our real life. All right.
So
All right.
the reason is just because of our assumption. It is not like we can't use it. It is like it will give less mistakes when we compare. It will be precise more.
No, obviously it won't be precise, all right. But then, if we have to study some compressible flow, all right. So if we initiate with it, so it will obviously give us a handsome idea about the flow. So
Okay.
it won't be like the results won't be away at margins from the reality. This is what I mean to say.
Okay. Okay, sir. Thank you. I got it.
Okay. Yeah, thank you. So it's also this one line has been mentioned in one of the slides of these lectures. Either it was in fourth or fifth or sixth. I don't precisely remember that slide, but this particular line has been mentioned in one of these lectures. All right.
Okay, sir.
Yeah, I have gone through these slides also, some previous year assignments. So I personally also worked these out, and based on that only, I'm telling you all this. All right.
Okay, sir.
So uh, I personally also have done this course way back in not actually way back, should I say? I have done it in my bachelor's also, and then in master's also. But then the particular question you asked, it's like it's very genuine question, I would say. But the your question, the thing clicked from your question was that particular slide from where I read this. So I'm based on that only. I am telling you. All right. There can be a very like detailed, good answer to that, but I believe for this moment it should suffice.
Yeah, because when I seeing that gas tables also they mention only isentropic flows.
Yes, 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 yes.
So yeah, because we
Yes.
have more type of like adiabatic, isentropic, also all
Y-
other, but we
Yes,
specifically talk
yes,
only about isentropic.
yes, 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 yes,
It
yes.
is not the reason because only in isentropic the entropy was constant. Is it one of the
No, no,
reason?
there has to be some reason to that, right? So if
Uh,
even if we are concerned with isentropy, why are we concerned with isentropy only? What is this particular assumption giving to us? All right, that is to be considered. That should be like our line of thought. Because plainly, because if it's isentropic, that doesn't mean anything. Out of blue we cannot say that because it's isentropic, and I to solve the mathematics of the compressible flows in isentropic only. That's why I'm doing it. Obviously there is some reason to that assumption on it to choose this path.
Yes, sir.
Yes.
I also interested in that one. Why they are choosing only this flow?
Yeah, yeah. So in my master's, so I have done this uh, low speed. I worked on low speed aerodynamics, and in compressible flows also in my PhD. But I am working on compressible flows already. In my master's, I was working on incompressible flows. But to your question, so I believe this should you should have you should get some idea from this, that because the assumption is not that at contrast with the reality. Very basic reason to that. All right. And to delve deeper, we will definitely will have to refer to the books. Okay, Yogesh.
Okay.
Yes. Let me take paper. All right. Okay. So let me just jot this down. All right. Yes, there is one more to the. All right, welcome to the new guest. So, we were discussing. All right, it's GIN Jin. My name is Aditya Sharma. All right, I'm from IIT Guwahati, and your teaching assistant for such sessions related to this particular course. All right, so we are at present discussing the topics that have been covered. Briefly, we will discuss those topics, and then we'll come to the problems for this session that I have in my slides, and we shall try to solve those. All right. Okay.
Okay.
So, all right. All right. So then we were just discussing isentropic flow, and Yogesh asked why we basically choose isentropic condition only. So we are discussing very basic level discussion we were having. So then uh, in isentropic this flow topic only. So we discussed we went through this stagnation condition. All right. Stagnation condition is nothing but the uh, in the slides, also in the lectures also it has been written this. It's also called the total condition. All right. It's one and the same thing. So denoted by let me just. So this is our stagnation condition. All right. So such uh, all right. Uh, all right. Jen, you need to say something. All right. All right. Okay. So we denote the properties linked to the stagnation conditions by a knot. All right. And, stagnation conditions are nothing but when the flow is not moving. All right. So in that case, the properties linked to that will be called stagnation properties. So when the flow or the fluid is at rest, and at that time what capabilities it hold, So that is basically stagnation condition. And then later in the slides, we went through the isentropic relations. So relations, isentropic relations related to uh, uh, pressure, all right, and then temperature and density. Uh, in the lectures, I believe, and we went through these relations. Okay, then we had this lecture 5. In lecture 5, all right, so we continued with the isentropic flow only. All right. So in isentropic flow, relation between static and stagnation properties. So in compressible flows, it's these equations at first are basic, but then these are very important, and they prove to be very handy when we are dealing with compressible flows. All right. So there are a lot of questions that are asked. All right, based on these relations. So there, I have a couple of questions, I believe, related to these uh, like properties and relations. All right. So later, then in the lecture 5, we went through 1D flow equations. 1D flow equation in lecture 4, we like basically we did some uh, basic juggling of properties related to 1D flow equations. So there we also discussed these three fundamental equations: the continuity equation, the conservation of, that is basically the conservation of mass equation, and then we discussed the momentum equation, and that is the conservation of momentum. All right. So then also we discussed the conservation of energy equation, that is basically energy equation. So energy equation linked to 1D flows only. So here we are mainly interested in 1D flows, all right, 1D compressible flows. So then a brief summary was given about these governing equations. All right. So this was it for second topic. Then we discussed the characteristic properties of compressible flows. All right, characteristic properties like characteristic Mach number. All right, a few 4 or 5 properties these have been discussed, and formulae related to these topics have been given in the lectures and discussed. So first was the characteristic Mach number. All right. So characteristic Mach number is there. Then there is maximum speed. So in compressible flows, with respect to like compressible flows only, we are discussing these topics. All right. So this characteristic speed is there. So characteristic Mach number and characteristic speed. All right. The characteristic speed is basically linked to this characteristic Mach number only. So because Mach number is V by A, so in that situation, if we have A star, all right. So this is characteristic Mach number, all right, which is M star. So this is V by A star, all right. So this is characteristic Mach number and the characteristic speed. So linked to that Mach number. So the speed linked to that is a characteristic speed. All right. Then speed ratios were discussed. All right. So this was U max. All right. And then this was A star, and this was A naught. All right. Stagnation speed of sound was there. So based on these three uh, properties, so we introduced some ratios. that prove to be handy when we are dealing with compressible flows. All right. And then there was this adiabatic ellipse. So as we know, all right, we have studied in our earlier classes. So equals to 1. Okay. So this is equation of ellipse. Okay, if I'm not wrong, this is the equation of ellipse. So then related to that only, we have this adiabatic ellipse for compressible flows, which is nothing but u by u max square plus uh, a by a naught square. All right, equals to 1. Okay. So this was mathematically this was adiabatic ellipse, and in this topic on the graph, various flow regimes for the compressible flows were mentioned and discussed, and we went through that. Okay, so this was about lecture 5, topics related to lecture 5, and then in lecture 6 we saw different forms of energy equations. All right, so energy equation, we saw different forms of energy equations that can prove to be helpful while we are dealing with the energy aspect of the compressible flows. Then there was, okay, so then there was pressure disturbances in compressible fluid. All right, so there we saw this concept of Mach cone. Okay, and then there is a region of silence. We went through that. So there is one formula related to Mach cone. All right, so this is sine alpha equals to 1 by m. All right, then we find Mach cone using this this formula. All right. So this was the mm, Mach cone. All right. So these were the topics that briefly we have been through in the week 2 lectures. All right. Lecture 4th, 5th, and 6th. Now we'll come to the main part of this session, that is the problems. All right. So there are theoretical problems, and then based on concepts related to the week 2 topics. And then there are numericals also. So we shall solve, all right, those questions. Okay. So let's move ahead in the session. All right. Okay. So before proceeding for this question, so I have jotted down the topics for like your current assignment. 10 questions are there. So there are for each question there is some specific topic that is or concept that is being used in that particular question. So I believe we'll try to like cover all those topics, and later if the time allows, so we shall briefly discuss those topics. We shall discuss those topics, all right. Based on those topics, the questions have been asked in the assignment, all right. because we I cannot solve the assignment questions in this session. So the tutorial questions should give a good idea of how to solve or approach questions that have been asked in the assignments. All right. Or other than that, it should also give a like hands-on experience to the students to solve the assignment questions. So this is the basic idea of conducting such live sessions. All right. Okay then. So I do have jotted down, but first of all, we shall go through the problems. I believe that would be better for us. All right.
Sir, I think your mic is muted.
All right. I'm sorry. All right. Okay. So I was saying that the first question is this is the first question. All right. So a 45-degree line with the horizontal passing through this should be through spelling mistake. All right. Okay. So a 45 degree line with the horizontal passing through the center of an adiabatic ellipse belongs to a m value of. So we have this adiabatic ellipse that we discussed in lecture 6. All right. So here we have the flow velocity. All right, and here we have speed of sound. So different regimes have been discussed, but the question says that if there is this 45-degree line is there, so in that case, what will be the value of m? So I believe I have placed some options. All right. So yes, please let me know the answer. Yes, Yogesh. Any idea?
So it's maybe one. No, I think subsonic is
Maybe
not just
one.
not just
You haven't gone through the slides, the videos, I believe, but that is fine. So there are regimes related to it. All right. So the Mac, I should tell you, the Mac increases in this direction. All right. So if we move in this direction, so Mac is increasing. All right. So the last part is for hypersonic flows. But then this, yes, the lecture tells us that for 45-degree, all right, this is C is the correct option. All right. Okay. Okay. Hmm. Okay. Then this is also a factual question. All right. So I would take guesses from you guys. All right. So when a space shuttle re-enters Earth's atmosphere, the nature of the flow regime is. I believe you all know these flow regimes. Okay, and out of these flow regimes, so when a space shuttle re-enters Earth's atmosphere, the what is the nature of such flow regime? So even when the space shuttle re-enters this atmosphere, all right. So we have heard this that the gases that are in front of the this space aircraft, all right. So even that the heat is of such magnitude that the even the gases they start to ionize, all right. So when the heat aspect is such that it cannot be neglected, all right. It's the when the heat this part is very substantial. In that case, uh, we need to define another class of flow regime when we are dealing with compressible flows, and such regime is known as this hypersonic regime. All right. So hyper and such situations arise when the Mach of the aircraft or space shuttle is spacecraft. I should say spacecraft is more than Mach 5. All right. So these regimes and the Mach numbers related to these regimes should be, I believe, on fingers. For compressible flows, at least we should not do mistakes in because when somebody interviews you related to compressible flows, so the fundamental things that he will start asking. So one question will be definitely will be related to flow regime. So we cannot do mistakes in such situations. Otherwise, it creates a very bad impression. So in compressible flows, I believe this is one of the pillars. Like if we want to like study compressible flows, so this is one of the fundamental pillars that we should hold fast. All right, in starting, I'm saying. So yes, so when the space shuttle re-enters, the flow is hypersonic. All right. So this is our answer. Then one can use the relation P plus rho u square. Rho should have been there, but it's gone to calculate uh, stagnation pressure of a Mach 5 flow. All right. So can it be done or can it not be done? So whether this statement is true or false. So yes. Any idea about this question? Jin, any idea about this question? Yogesh, any idea about this question?
I think it's true
It's true. All right. So
because
okay.
we have given the initial velocity. Anyway, Mach number is equal to u by a.
All right. And
We can substitute u is equal to a by.
no. It's not from that perspective.
Okay.
It's from that perspective that this value, this whole value, does it correspond to the stagnation pressure when the Mach is 5? So see when just I discussed that. the flow regimes are very important, right? So as the flow regime changes, the mathematics related to it also changes. All right.
Okay, sir.
So all right. So for Mach 5, the things become hypersonic first of all, right? And then P plus rho u square is related to this momentum equation, all right? So can we calculate the stagnation pressure for Mach 5 using this relation? So we are concerned basically with this relation. So is this the relation for stagnation pressure when the flow is 5 or more? All right. So the answer to that is no. Okay. We cannot use this particular relation to to get to the stagnation pressure related to Mach 5. All right. Okay. Then I believe. Okay. So this is a
Sir, I
yes.
got little connection issue. What was the answer to the last question?
False. 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 All right. False. False was the right. So we are also like uploading these sessions on YouTube also, right? So because in last session the recording wasn't like up to the mark, so I just recorded it once more as a monologue, and then I uploaded it on YouTube. So these sessions will definitely go on YouTube. So later, if somebody wants to like go through these discussions, he or she can go through it. And if someone prefers to join while the session is live, that is also welcome. All right. So even if you miss something, that the links to the recordings will be provided to you. I believe the first this link has been provided. All right, I saw the notification also. So we shall move to our question. This next question. All right. For Mach 5 air, all right, gamma is specific heat ratio of gamma. That is gamma. Sorry, it's 1.4 value of gamma has been given and Mach of 5 has been given. All right. So the ratio of kinetic energy to the internal energy is. So we'll solve this. Okay. All right. So we have this our question, right? And the solution. So kinetic energy. We have been asked kinetic energy divided by what? Internal energy, right? Let's have it. Okay. So for kinetic energy per unit mass, we can write kinetic energy as V square by 2. Okay. Please let me know if you feel that there is something wrong in the mathematics. All right. So, okay. And then internal energy is nothing but CVT. All right. Specific heat at constant volume. And then temperature uh, in hand. All right. So it becomes what? V square by 2 divided by this. The formula is the CV's formula in terms of gamma we have, right? That is 1 by gamma minus 1 into r. All right. And then this t is already there. Okay. So if we rearrange the terms, okay, keep your calculators, please keep your calculators handy. So I shall ask you guys to give me values. Okay, so this was it. We reached to this point, all right. But then what is given? What has been given in the question? We have been in the question we have been provided with Mac, all right.
Mac and gamma.
Yes, yes,
Mac equal to 5.
yes. Mac is given, and then gamma is also given, right? Gamma
Yeah,
is
gamma 1.4. 1.4.
1.4. But then you see, if you see in this uh, expression, all right. If you see this expression, we want we have v square, all right, but we want m. Okay, but we know, what do we know? We know that m is v by a, all right. So we'll just try to be a bit creative, all right, because in the denominator term we have rt. Okay, so if this thing doesn't click to you, then solving this problem can be like be a difficult or a challenging task. But then what we will do, we have this expression, all right. We have this expression in our hand, which is gamma minus 1, right, v square divided by 2rt. So but we know what. So in denominator we want, right, if you see this denominator, all right. So if we can somehow have a square here, all right, so it will become m square. So what I'm trying to say is, so if I can have a denominator a square, then it will become, m square. All right, this value is nothing but m square. So we want this here. We want this here, all right. So what we will do, but we also know that a is nothing but gamma rt root, all right. Okay, so if we square both sides, this is gamma rt, all right. Now rt we have here, all right. We want gamma, so what we will do in the expression, what we will do, new expression, gamma minus 1 v square, we'll keep it like this only. We will multiply the numerator by gamma and denominator by gamma, all right. Now we have this thing we have, all right, this thing we have, and there is no harm in including numerator gamma in the numerator side, because we already know the value of gamma. We didn't know the value of v, so we are like redefining the expression, all right. So then it becomes gamma minus 1 v square, all right. So gamma rt will become what, a square, right. This we have already seen here. Okay, so okay, Just wait a second. Okay. So this will become a square and then 2 is there. Alright. So it will become gamma minus 1 by 2 divided by a square. And there is gamma also. Alright. There's gamma also. So it becomes gamma into gamma minus 1 divided by 2 into m square. Alright. Okay. Which is nothing but 1.4 into 0.4 divided by 2 into 5 square. All right. Now please
Answer is
work
7.
this. Yes. All right.
Answer is
Answer is 7. All right. Okay. What happened to this? Answer is 7. All right. Yes. So Jen, you are also getting the same answer.
Yes, 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 7. I got it.
You got it. So all right. So I'm pronouncing, I believe, your name correct. Please let me
Yes, my
know.
name is Ginny. Yes.
Ginny. All right. Ginny. All right. Thank you. Okay, then we'll move on to our next question. Solution related to that. Okay. No. All right. So answer is 7. All right. You have the answer, and we saw how to solve this particular problem. Then we'll move on to next question. Okay. Okay. So we have another question. The supersonic stream of air is moving at a Mach of 2 in the test section of a wind tunnel. The Mach angle for this flow is. So please work this question out. All right. It's a very straightforward question. So Mach is given is 2. We need to find Mach cone, which is also alpha. Let's call it alpha. Okay then. So we have seen that sine of alpha is equal to 1 by m. Right? Then alpha is so 1 by 2. Then okay, then what will be the answer to this? Yes, I need an answer.
3.4.
3.4. Okay, all right. So I believe what you did is okay. So Ginny, So here we have this inverse trigonometric relation, all right?
So for me, it's coming
Yes.
30.
Yes, all right. Okay. I shall discuss this. Then we have this value of sine, all right? So if we this table, so even we need not to use the calculator, all right? So if we
Yes, 30.
see,
Yes, 30.
yes, all right, 60 and 90. This part is very problematic. Okay, 1 by 2. If I remember it correctly, it is this, and this is root 3 by 2, and this is 1. We need not to use the calculator anymore. So there can be like while you're using the calculator, you need to be sure that the things are either like you are proceeding keeping in mind that your answers will be in radian or keeping in mind that your answers will be in degree. So you need to configure your even calculator related to that. Otherwise, mistakes can be there. All right. But Macon, I must say, is a very interesting topic. Very like very fundamental topic, but also very interesting topic. Okay, so so like in last lecture we discussed, I believe, pressure disturbances, or there is some topic related to that. So in that we see how the like pressure waves proceed when there is an object is moving with supersonic velocities, velocity that is greater than the speed of sound. So how sound waves behave in that fashion. So all these questions are related to that only. Right? Okay. So 1 hour has passed. All right. So I believe we should take 5 minutes, quick 5 minutes break, and then after that we shall proceed further. Okay, is this all right with everybody?
Yes, okay.
Okay,
Yes, sir.
okay then. 5 minutes break and then we will proceed further in the session. Okay, then I believe we should proceed further with the session. So, if Ginny and Yogesh are there,
Yes, sir.
Yes,
okay,
yes, sir.
okay, thank you. So, let's see the next question. Hmm. An aircraft is cruising with a Mach number of 1.5 at an altitude of 1000 meter. Okay, just wait a second. Okay, so an aircraft is cruising with a Mach number of, all right, 1.5, all right. Mach number here is 1.5. Let's just underline this. And this altitude is 1000 meters. All right. So while watching the aircraft from the ground, the aircraft moves in a flyby. All right. Okay. So while we are watching from the ground, the aircraft moves in a flyby. After how many seconds the aircraft passes the overhead, one can hear the sound. All right. So, and there is an aircraft which has just passed over our head, all right, over us. So, but then it's moving with a velocity that is supersonic, all right. So, in that case, the sound we shall witness of that aircraft. So, obviously, because the aircraft is supersonic and the sounds we listen reach us at the speed of sound, all right. So there will be a lag because the aircraft is moving with the velocity that is greater than the speed of sound. So even if in blasts also, you see, like if you visually see a blast, so from it, the like handsome system, if you see visually a blast from a handsome system, you'll see the visuals you can see of the blast, but then the sound has not yet reached to you. So that is also like related to this question only, all right. So we have this aircraft, all right. Let's just draw one aircraft. Oops, something like this. All right, something like this, something like this. Okay, so we have this aircraft, and then we are just standing right below this. Okay, we are on the ground. Then, so what concept we will use here? So the concept that we saw in lecture 6. All right. So this pressure disturbance when an object is moving with a velocity that is greater than the speed of sound. We just also solved a question related to that only. Alright. Now this thing has been given to us. All right. So it is moving with a Mach of 1.5, and then this height has been given to us. Let's call this height as h. All right. H is given to us. We are 1000 meters below this aircraft. All right. Or this aircraft is 1000 meters above us. Okay. And then something else is given. Okay. So speed of the sound is also given to us. Right. So speed of sound has already been mentioned to us. We have Mach and we have this H. All right. So what we shall do here? Hmm. So if you draw the Mach cone of this aircraft, all right. I am doing it a 2D. It's a 2D drawing because it's a plane sheet, but in reality, it will be a cone-like, right, formation. But then if we see in just one plane in which there is aircraft and in which we are there or this person is there. So in that uh, case, this particular drawing will suffice. That will do our job. All right. So this is the Mach cone we know. All right. Let me do this. Alpha. So because this is alpha, then this will also be alpha. All right. Okay. All right. Then what to do? Because this question says that, like I already discussed this, the speed related to this aircraft, all right. So it will definitely have a lag because we see when let's see there is this fluid, all right. Let's see there is this sheet. The right side of this sheet is our fluid, all right, or air. Let's suppose atmosphere. So if there is disturbance, pressure disturbance, or at this point, so it will propagate in all directions. Okay. So in the form of sphere, it will propagate. All right. So, but for representation, I'll just draw a circle here. All right. So with passage of time, the circle will increase. All right. So at some time t, because this speed is propagating with the velocity or the speed of sound, that is acoustic speed, which is a. So at some particular time, so this distance will be a into t. All right. This radius will be a into t. A into t. Okay. A into t. Okay. But then our aircraft just every time in the this atmosphere, it creates some disturbance in the form of sound. After creating that disturbance, it just escapes that uh, this circle. All right. This uh, this uh, this particular circle. All right. Mentioned. So initially the aircraft will be in this circle, but there will be time when aircraft will be like this. So something like this. Aircraft will reach here, all right? So in that scenario, you will get this Mach cone. So these circles are basically correspond to nothing but the this Ginny, you want to ask something?
No.
No. All right, all right, all right. So all right. So what I was saying is that all right. So at times it will just move out of this disturbance that it itself has created. All right. So it will move in that fashion, and will in this whole its course it will keep on creating this disturbance. But then we have to keep this in mind that this disturbance has some speed. All right. So the structure this type of these type of disturbances create is in the form of this type of cone. All right. So we will listen to fundamentally or basically what we listen is because of these disturbances. All right. Even what you are listening at present is also a disturbance that is propagating in this fashion only. Like from this my Adam's apple only I am creating some pressure disturbance, and this pressure disturbance is moving it in this fashion only. All right. So until and unless this disturbance reaches you, you won't be able to listen anything. All right. So when an aircraft moves in such fashion, or when our aircraft moves in such fashion, so it creates this type of cone. All right. So this disturbance as it passes over our heads, this disturbance won't reach us. Okay. So even this aircraft will proceed further and we won't listen anything. But then there will be case, a time will come when this point, all right. So this whole whole thing, if you see this big cone, it will keep shifting right, all right, as the aircraft moves forward. And there will be point when this particular point, all right, this particular point will reach here. All right. Okay. At in that time, we will listen the first sound related to uh, this aircraft. All right. So then, what do we need to find out? We need to find out at in like how many seconds. All right. So for seconds, this point, this point has to travel to this point. All right. So this distance it has to cover. Okay. And this distance it will cover with what speed? With the speed of this aircraft, because obviously this whole cone is moving with the uh, aircraft only. All right. So that is the, and the speed of aircraft will be the speed of this particular aircraft. All right. So this particular distance, let us call this distance what, d. All right. Let's call this distance nothing but d. All right. So we have this distance, and then we have h, we have m. So now we will proceed for this. Uh, we can proceed to solve this uh, question. All right, numerically. So let's see this. All right. Okay. So Mac is given 1.5. All right. Then we have A is 343.3 meter per second. All right. H is given equals to 1000 meter. All right. Then we don't have this Mach cone, because if you see our diagram, so how can we find out D? If somehow we know this alpha, all right, we can have, we know this tan is equals to height by base, all right, height by base. Height here is h and base is t, all right. So d distance can be found out with this, okay. But then we need to find alpha for that, because there will be otherwise two unknowns in this tan alpha equals to h by d, because this is unknown and this also is unknown. So we need to find d also, and then only we will be able to like proceed for our answer. But before that we need to find alpha, because that will give the d. Okay, I believe there is no confusion in it. If so, you may ask please. So we'll use this expression for Macon, sine inverse of 1 by m. Okay, sine inverse of 1 by 1.5. Now please use your calculators and let me know what this value is.
41.8.
41.8. And what is Genie getting?
Yes, 41.8.
Right. Okay. So 41.81 is right. So I have also like worked this out. So that is right. So now we have tan alpha, we have alpha in this expression. All right. Then let's just work this out. Tan of 42 degrees. Let's just write 42 degrees equals to h by d. All right. Implies tan of 42 degrees equals to 1000 divided by d. Okay. So implies d comes out to be 1000 divided by tan of 42 degrees. Yes. So what's the answer?
1 point.
1.11.
The whole d.
Yes.
The whole d is
1.11.
1.11 what?
Wait, 1110 meter. 10.6
Yes.
meter.
See, tan, because you see tan 45 is 1, right? If you see
Yes.
tan 45 is what? 1.
Tan 42
So
is 0.9. 0.
so tan 42 will be less than 1, all right? So if there is denominator that is less than 1, then d has to be greater than 1000, because numerator, when numerator is less than 1, the when the denominator is less than 1, then the numerator's value increases from its current value. All right. So, all right, Ginny.
Yes, is one. Okay, 111.1
Yes,
answers.
111. Yes, yes,
Yes.
yes. This is 1110.61. All right. This is the value. So this is T. Okay. All right. Now, the question is almost solved, right? We have distance. Now we need time. So as I already told, that the whole cone will move with a speed that is equal to the speed of this aircraft. All right. So we'll use a very fundamental. Oops. Yes. Right. This is correct. All right. Because we need to find time, and this is the expression for time. All right. And we have this. All right. As this. But we need to find this, which we don't know. Or do we know? Obviously, we do know this because speed is what? All right. Should I say write it like this? Wait. Should I write it like this? Okay. Mach is V by A. This is the speed. This is the speed. All right. This is given 343.3. Then implies V equals to M into A. Mach is 1.5 into 343 point what? 3. Okay. Yes, give me this value.
514.9.
Yes, Ginny.
Yes, 514.9.
Okay, thank you. So, so here we have this value. All right. So our time will be distance upon speed. That is 1110.61 divided by 514.95, and this comes out to be, yes,
2.15 seconds.
okay,
2.15.
yes, 2.156, we can say 2.16 seconds. So we have time. Answer. Right. Okay. So this is our answer. All right. Then. All right. So this is clear. All right. This question is clear. Any doubts?
Yes.
No. Okay then. Then let's move on to the next question. Okay. So there is this information given. Based on this information, we have to solve these two questions. The next two questions will be based on this particular information. This particular information. All right. Based on that, we shall see. Okay. All right. Let me just switch on my light. Right. All right. Okay. So we move on to our next two questions. All right. Then this we have here is helium gas. All right. This gamma is given here. This is nothing but gamma. All right. Writing it poor gamma. So helium gas is to be discharged at, we have helium gas, we have gamma 1.67, and it is to be discharged at sonic velocity. All right, what is sonic velocity? Sonic velocity,
One.
yes, all right, thank you. When Mach is 1, nothing but when Mach is 1, into the atmosphere, where this atmospheric condition is 1 bar and 300 Kelvin, through a constant area duct, right? Through a constant area duct from a reservoir. So we have a reservoir. Let's say this is the reservoir. And then we are moving here in a constant area duct. Right. This is our constant. Okay. Okay. The constant area duct, and then we have here outside we have 1 bar and 300. So these all things have been provided to us. All right. And gamma obviously is 1.67. So there are two questions. So these questions are basically based on isentropic relations. All right. Okay. So the minimum reservoir pressure is all right. Okay. So we need to find P naught, all right? Because the reservoir pressure has been asked. We need to find P naught. How do we find P naught? Yes, any idea? How do we find P naught? So we have these isentropic
P.
relations, right?
Yes.
Yes?
P by
Yes, yes,
P naught
please.
is
Yes, 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 yes.
gamma. T by T naught, the whole power gamma by gamma minus 1.
Right, 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 right. Okay, okay. So I shall just write this down, all right? So T naught by T is what? 1 plus gamma minus 1 by 2 m square. Then this is T naught, right? Then what is P naught by P? Is nothing but T naught by T by gamma minus 1, right? this is for, and then there is also for, which is nothing but P naught by T 1 by gamma minus 1. Alright. So these are the isentropic expressions. Isentropic relations. Just you'll use these and solve it. So P naught by P is plus gamma minus 1 by 2 m square gamma by gamma minus 1. So gamma has been given. And because it's sonic, so m will be 1, right? There is no doubt in it. And then okay. So this comes out to be yes. This value comes out to be how much? This inside the bracket.
Is 1.335.
Yes. All right. So this comes out to be
Is 2.0545.
okay. And Yogesh? Yes, Yogesh, are you there?
The same answer comes from.
So it's 2.05. All right. Implies P naught this is this. Then we need to find minimum what? Reservoir pressure. So that is nothing but the stagnation pressure, all right? Because in the reservoir, the helium gas will be in the state of rest, and that is the definition of stagnation pressure. All right. All right then. So P naught equals to 2.05 into P. What is the static pressure then here?
I think 1 bar. It was given in the question.
Yes. So from the reservoir, let's just see the question so we can just visualize. So if we see this para, two lines or just one line. So the helium gas is to be discharged at sonic velocity. So velocity we have sonic, all right, into the atmosphere. So okay. So eventually the helium gas will have this static pressure of 1 bar, right? This means that. So 2.05 into 1 bar, all right, which is okay. So this is our answer. Okay. So any doubt in this question now? This was straightforward, right? But just you have to take care of this thing, that you should know that the reservoir pressure is the stagnation pressure, and at the end the static pressure will be equal to the static pressure of the atmosphere. The static pressure of this uh, flow, the sonic flow, will be equal to the that of atmosphere. All right. Range has been given. So 2.04 and 2.07. So our answer is 2.05. That falls in this range only. Okay. Moving on to next question. This is also straightforward. Please work this out. Right. I'm also working this out. Into T.
Answer is 400.5.
Yes. Jenny got the answer too.
Yes, I got is 399.
Okay.
Oh, it's 3.
That is fine. All right.
It's
But
400.
you just have to be in the this appropriate range as the question
Yes,
asks.
400. Yes, yes, it is like 400.5 it is coming. If I consider
Ye-
1335.
Yes, yes, yes. Based on what level of accuracy the question asks. All right. In the gate, they
Okay.
they specify decimals. All right. Like up to
Okay.
1 decimal point or 2 decimal points. So like if you will start ignoring your decimals from the beginning of the solution of the question, then this gap becomes too much eventually when you get your final answer. And then there can be there are chances, there are very good chances that you will miss that range. all right, even when you know the concept and like you have solved it correctly. So just
Okay.
in starting, just don't ignore the decimals. At least up to three decimal points, you solve your problem.
Okay.
Okay. Okay. You may switch off your mic. Thank you. Okay. So like here we have a good range. So even 399 would have been a correct answer. Moving on to next question. So up to this point, these questions were asked in the 2020 assignments of 2020 assignment of this course, Fundamentals of Compressible Flow. All right. So because this course started, I believe, from 2020 only, and at that time these questions were asked up to this point. But then I believe there are one or two questions in the questions we have discussed that are from my side maybe. But mostly these questions up to this mark are from the previous year, like 2020's assignment. All right. So these few fill in the blanks are from my side just to so that we can revise the theory of these lecture 4, 5, and 6 uh, topics. Okay. And then if the time allows, we shall have a brief discussion, or just we shall see the topics that cater to the questions that have been asked in current assignments. All right. I have already told you that I'm not going to, like, I'm not supposed to solve those questions. But then we can at least have discussion on the topics they are based on. All right. All right. So fill in the blanks type questions. Uh, I would expect you guys to like answer these questions. Otherwise, I will discuss it. All right. Anyways, I'm going to discuss it. So for compressible flows, all the governing equations need to be solved along with. All right. So this is basically related to this when we are trying to solve the mathematical equations, these governing equations, and we are trying to find solutions for uh, these equations. So such equations are like such knowledge is useful in this computational fluid dynamics. Computational fluid dynamics is very, 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 very extremely important as far as the fluid dynamics is concerned, right? The maths of fluids is very important. It's it's same as tracking the behavior of flows, all right, mathematically. It's very beautiful. I personally find it very beautiful, like the CFD, compressible, this computational fluid dynamics, all right. So from that perspective, CFD is very important, and I would suggest, like, even like those who are interested in fluid dynamics must take computational CFD very seriously. At least they should do some course on computational fluid dynamics. All right, and try to do things in practical also. All right. So when we yes, Yogesh.
Okay, the answer is not the computer.
Sorry.
For the question, the answer may be Navier Stokes.
No, 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 no,
No.
no.
Equation of state.
Yes, yes. It's from the this lecture slides only. Equation of the state. All right.
Yes.
Nothing. Yes. So you have gone through the videos. Equation of state. So these are from that only. But along with that, we just discuss the things related to such fill in the blanks. All right. So that it is not too much. The session doesn't remain too much in numbers, so that we can discuss at least the physics related to the flows. So in reality, what is happening? All right. So yes, the answer is equation of state. So in that slide, if you see, so that has been said from that this perspective only, CFD perspective only. Like there, it has been said that for incompressible flows, the equations need not to be coupled. All right, the pressure and velocity terms need not to be coupled, and then for compressible flows, these need to be coupled. I believe this has been said. So this is from that perspective only. Anyways, these equations are solved like using integration and with hands only. It is also done, but then there are numerical techniques with which we solve these equations. All right, we deal with these equations, and that is also to be considered very very seriously. All right. Okay, equation of state. Then yes, what will be the answer to this fill in the blank? The flow can be considered as dash if the heat transfer as well as the frictional effects are neglected. Yes. Okay, so if there is no heat transfer, it will be adiabatic, all right? And if there is friction comes into the picture, then obviously heat will also come into the picture, all right? Because of friction. But then when they are neglected, the flow in that condition can be considered as yes. Syndrome. Okay. Yes, yes, yes. Yogesh, please switch off your mic. All right. Yes. So the flow can be considered as isentropic, all right? The answer to this fill in the blank is isentropic. So if there is no heat transfer or frictional effects,
So, are you
then
presenting the screen?
sorry,
Are you presenting the screen for me? It's nothing.
I am presenting.
Maybe I have some internet issues.
No, 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 no. Maybe wait then. Do I try to like present it once more? Do I do that, Yogesh?
Now it's visible.
Okay, I'll just let me.
No, so now it's visible. Now I can see.
Now it's visible, right?
Yes.
All right. Okay, then that's good. So the flow can be considered as isentropic if the heat transfer as well as frictional effects are neglected. All right. So isentropic is the answer to this, fill the blank. Okay. So I believe this is the last fill in the blank that I had planned related to this session. So compressibility effect can not be neglected for M when M is greater than. Yes, that's also very
1.
okay. You are saying one. All right. And what does Yogesh say? Yes, Yogesh, are you there?
0.3.
Okay, Yogesh says 0.3. All right. It is factual, all right. It is factual. So if you have read it, you'll be able to answer it. And if this has not gone through your eyes, you won't be able to answer it. So the answer is 0.3 only. All right. So for Mac values greater than 0.3, all right. So for such situations, M can this compressibility starts coming into picture. All right. So this is factual, but this you should know, like because we are studying compressibility, and you must know that what is the value of a Mach number beyond which the compressibility of the flows cannot be neglected. Yes, we call the flows subsonic from 0.3 to 0.8. All right. And all right, but I have to discuss flow regimes also, right? Just just for my so time is also, I believe, which time is also, I believe, over. So I shall take maybe just 5 minutes if that's not a problem, right?
No problem, sir.
Yes.
Yes. Okay, okay. And we shall conclude this session then. So compressibility effect. So this is Mach number is 0.3. All right. So this is what I was saying that when Mach number is from 0.3 to 0.8. All right. Then we do say that the flow is subsonic. But then from 0.3 onwards, the compressibility effects these start coming into picture slow and steadily. So you cannot you cannot say that if the flow is subsonic, then it will always be compressible. Its speed will be less than the speed of sound, but then there will be compressibility after this 0.3 value of Mach number. All right. All right. So I have come to this. Okay. So this is our answer. All right. So I have come to the conclusion of this session. All right. All right. Then. Okay. All right. So in this session, what we did, just to conclude, as we will be doing in other sessions also, all right. We will be just in beginning. We will be discussing the previous week's topics that have been covered in the lectures, and then we will be doing some uh, these assignments that have been given to students in the previous versions of this particular course. And then, if the time allows, we will be doing the fill in the blanks type of questions. All right. Uh, this is at present, this is in my mind. I'll proceed in this manner for the coming sessions, but there obviously there are there is space to evolve. So if we think that we need to add some things in the session for the betterment and quality of the session, so we can obviously move in that direction. All right, we can add different things to these sessions. So this was also discussed, like these things also were discussed in today's session. So we discussed week two's topics, and then some previous year questions, and then we discussed some fill in the blanks type questions, and that's it. So we conclude today's session. All right. Thank you. Happy learning. And we shall meet in next session. All right. Same time, same day. All right. Okay.
Okay.
So
Okay.
thank you then. Thanks for attending this session.
Thank you.
Okay.
Whether these slides will be available
These will be
again.
all the content will be available. Also on these recordings will be available on YouTube, and the slides will also be available on the Google Drive link that has been shared with you guys just, I believe, yesterday. There has been
Okay.
shared one Excel sheet in which there are these YouTube links of these sessions, and there is one also Google Drive link. So in this
Okay.
Google Drive link, there will be these slides. Fine.
Okay. Okay. Thank
All
you.
right. Thank you.
Thank you.
Thank you, Yogesh.